As visualization developers, the ways that we present data can fundamentally change the conclusions that people draw from the exact same information. As a result, we have an ethical obligation to make sure we're presenting data as faithfully as possible. Doing so is often easier said than done, and there are a host of reasons and considerations that we might use when trying to decide what's the right way to represent our data. For this particular lesson, I would highly encourage you to check out the readings that are linked on Coursera for an in-depth discussion of things like data semantics, visualization mirages, and other interesting concepts that pertain to fundamental questions to ask yourself when building ethical visualizations. For the purposes of the video lecture, I actually want to stick with a fairly straightforward hands-on activity where what we're going to be doing is trying to take a critical eye towards our visualizations and identify common misleading practices that may occur while presenting data. When you're creating visualizations, I would encourage you to internalize the idea that your visualization should show the data as faithfully as possible. Ultimately, as faithfully as possible is a gray area. You want to try to show the data in as objective as possible way, but people are biased by their own prior knowledge and interpretation, and also the ways that we represent the same data may inherently beget different conclusions about that data. What I would instead encourage you, instead of going for a perfect, honest representation, is to think about your obligations in building visualizations as a form of almost a Hippocratic oath. So you'll practice two things in your dealing with data: either help or do not harm the analyst. There are a number of really interesting questions in this space in terms of how do we do ethical data visualization, and I've linked a number of readings that will provide you with interesting insight and background into this challenge. But what I want to walk you through in this module is practices that can create dishonest visualization that occur fairly commonly in visualizations that you'll see in the general public. For each of the way we're going to run this lesson is that I'm going to show you a series of examples. And for each of these examples, what I would like you to do is pause the video, reflect on the example, and figure out what biases might be present in each chart and how you might fix them. A quick heads up, some of these examples may have multiple biasing factors. So we'll walk through the big ones to help you understand what are some rules of thumb for honest practice in visualization. So here's the first example that we have, and I should note in advance that many of these charts are replications of charts that actually occur in the wild. So these are unfortunately not just examples that I've created for this course, but these are replications that have been anonymized to protect the source of common, often infamous visualizations. So in this case, I have a pie chart of polling data. This is in purple, the percentage of polled participants who back candidate A, the percentage who back candidate B, and the percentage who back candidate C. So pause the video and take a moment to think about what might be biasing in this image. All right, so this particular example hopefully isn't too intense. When you look at this visualization, you think that, all right, roughly a third of each of my polling sample back each candidate. But if you actually read the numbers on this pie chart, you'll see, well, 70% backed candidate A, 60% candidate B, and 63% candidate C. If I add these values up, these add to much more than 100%. And this can be misleading. People tend to expect that proportional representations will add to 100. So even in cases where it's not misleading, you're still going to confuse people as to what the chart is actually trying to say. So in general, the fix for this is that we should adjust our pies such that pie charts or other proportional representations always sum to 100%. For the second chart, we have the percentage of agreement on a particular topic. So I have the people who agree represented in blue and those who disagree represented in red. If you haven't already caught on to the misleading practice here, I'm going to give you a hint and show you the title of this chart, which is truncating the y-axis misleading? Well, that hopefully illuminates something for you. Even though at first glance it looks like the blue and the red area are roughly the same, so you would expect about 50% agreement, if we look at this y-axis, we can see that the y-axis itself starts at 99%. So 99.5% of respondents agree that this particular question is truncating the y-axis misleading. They'll say yes it is, whereas 0.5% say no it is not. But if we look at this at just face value, we would expect it's about a 50-50 division. And one thing that you will find in practice is that people often do not read the y-axis. So we see these kinds of examples in popular media as well. So here's an example that's been replicated from a major magazine showing law school enrollments over time. And the argument behind this particular example was that large-scale law school enrollments were in the tank in 2013. So if I look at this chart and I don't pay attention to the axis, I would think there was almost no one in law school, that law school enrollments were near zero, but anyone who's set foot on a college campus knows that this probably isn't the case. And in fact, if we look at the axis, we can see that law school enrollments in 2013, while significantly declined, were around 40,000. So what does this mean? Well, if I choose to represent this data without the truncated axis, I get a pattern much more like this, where I see that, yes, I still see this sharp decline, but in reality, there are still many students in the classroom. So in practice, what this means is that our y-axis should, generally speaking, start at 0. I have students come to me frequently arguing about, well, if I don't truncate my y-axis, if I started at 0, my data might be so skewed that I can't see smaller variations in that data. In those cases, what I would encourage you to think about is your graph actually showing the data it should be showing? If what you care about is change or fluctuations in the data itself and those small scale differences, it's possible that what you actually want to be showing on the y-axis is the percentage change, not the actual raw values themselves. So if you find yourself truncating the y-axis, take a minute to more deeply consider if your visualization is actually looking at the data in a way that lets you answer the question that you have. So this next visualization is a replication of a visualization that was used to argue for legislative change in the United States Congress. So this chart shows the number of services offered by the organization Planned Parenthood, with preventative services shown here in pink and abortion services shown in red, and the x-axis represents time. One thing you might note at this chart is that the most salient thing, the thing that's most visible, is this crossing right near the middle of the chart that shows abortion services exceeding preventative services. And again, not a political course, but if we look at the raw numbers that are shown in this chart, one thing that you will notice is that here, after the red line is above the pink line, we see that the value of the red line is 327,000 services, and the value of the pink line is 935,000 services. So what this tells us is that even though the red line is above the pink line, in practice, the pink line's value is roughly 3 times that of the red line. So what does this tell us? Well, it tells us that this crossing is creating this false sense of exceeding, this false sense of change in quantity, because the y-axis represents 2 very different scales. So if we instead map this data to a more common y-axis, so here I have preventative services on the y-axis in terms of raw numbers, millions of services, what I can see is that there has been a significant decline in the pink line and a slight increase in the red line, but that the value of the red line is still much smaller than the value of the pink line. So the fix for this is that all of the data in a chart should share the same axes. You might run into designs called dual axis plots that take advantage of these same kinds of ideas, where I have different data dimensions that are mapped to the y-axis. One of the tricks there is if you want to overlay your data in a way such that the units of the 2 axes are not the same, you should adjust the ratios of those units on each of your axes such that they're comparable. That is, you don't want to have drastic differences in magnitude creating artificial differences that may or may not exist in the change of values of our data. In general, though, it's just simpler to have all data share the same axis and each axis share the same units. One other thing I want to call your attention to on this chart is an issue that's raised by Draga and Voss. So Draga and Voss, in their discussion of the technical inhumanity of illustration, in particular is a paper they call Cruel Pies, argue that by showing data about human life, human well-being in terms of abstract values, that you're actually creating an ethical conundrum. Is it okay to represent data about human beings using just abstract values? So one thing that people might do to try to overcome this is they might do something like adding a graphic that shows a baby or a person. One of the things to think about here is that these kinds of graphics have persuasive power. By showing this imagery, you're evoking a certain affect to the data, and you're coloring the context within which this data is interpreted. This is a technique that is known as chart junk. You're just layering additional information on, and that information may shift the interpretation of the data by doing things like introducing alternative affects. One other thing that chart junk can do that's a much simpler issue is that chart junk can actually do something like occlude a particular set of values. For example, I have no idea what's going on in the pink line here. So in general, it's a good rule of thumb to avoid including any sort of information that doesn't actively help you interpret the data. So we can take that chart junk out, we can see the data much more simply, and we can make much more direct and objective comparisons about what's going on in the data. So the simple takeaway from this additional fix is that images can carry persuasive power and also add unnecessary clutter. So in general, it's a good idea to avoid chart junk, to avoid this extraneous imagery that doesn't actually represent the data. So this is another chart that is intended to show changes in value over time. We have time on the x-axis, value on the y-axis, and this is just data simply across 4 years. It's actually a fairly simple data set overall. So take a minute and explore what biases might be emerging here. We can illustrate this bias in a very simple way by the fact that year 1 actually appears much larger than year 3, when in reality, if we flatten out our data, what we can see is that those two values are exactly the same. The trick here is that visual perspective and depth on traditional monitors, print media, anything 2D is not really very effective. It might look cool, it might seem fun, but what it's actually doing is distorting our ability to estimate what is going on in our data. And that can get even worse when the third dimension is used a little bit more rigorously. So for example, here I have a 3D bar chart. And not only is it difficult to try to project data values back against these different axes, for example, is this bar back here the same value as this bar up here? Well, it's not so clear. But you also run into issues where you can have what is called occlusion. For example, I can't see any data behind this clump of bars here, and it's very, very difficult to see this small bar up front. So what we can do is when we have data that exceeds 2 dimensions, we can explore other visual channels for representing that data. For example, instead of using this 3D bar chart, I could use something like this particular chart here where I use size instead of depth on the z-axis. So instead of that third dimension, I'm just using smaller or larger bars. And here I'm using color for the exact same comparison. And what this is going to do is it is going to make it dramatically easier to make comparisons between different values because I'm not having to mentally project from 2 dimensions to 3 dimensions. But it is also going to avoid this occlusion issue where I lose my ability to actually even see some of the data that occurs in my data set. So the fix for both of these is don't use 3D unless it is absolutely necessary. So there are a ton more rules of thumb that exist for honest and faithful data communication. We'll talk about, for example, the need to avoid rainbows in the color section. But just to give you a quick synopsis of what we talked about here, if we have pies or other proportional representations, those should always sum to 100%. Our y-axes should always start at 0. All of our data should share the same axes, and those axes should be scaled accordingly. Images can carry persuasive power, and they can also add clutter, so we want to try to avoid chart junk. And we also want to try to avoid 3D. While it might look fun and cool, it can create issues like occlusion and errors in perspective projection that just make our data hard, if not impossible, to read. As I mentioned, there are some more nuanced discussions around visualization ethics that I've linked in the readings that I would highly encourage you to think through, both in terms of the paper that I mentioned by Draga and Voss, and also some more recent work exploring different ethical questions that should be asked in the context of visualization design. These are fabulous areas for discussion that I would encourage you to explore in depth more in the discussion boards and through discussions with your colleagues both in these classes and others.